Hello, everyone. So today is summer solstice. It's very meaningful holiday in my life. I don't know whether it's very meaningful in your life, but happy summer solstice day, and wish you all like observe the sunset for today. It's very beautiful, because it's the longest day across the year. Okay, so remember last time we have covered mathematical induction and also recursion, and we show some examples of recursion, which is we can see here, which is Fibonacci sequence and also some summing of different elements, product of elements, factorial, and those are a good example. And also the walking from the steps, in the steps getting one step, another step, which is good recursion. Also, there's many examples of mathematical induction. Like in this case, we are doing mathematical induction in real number computation, and this is a power set example. So before getting into today's topic function, I would like to introduce a new example as the power set example of a recursion. So first, let's define A1. Let's define A1 here, which is 0, 10, has two elements. So you might say, well, it's pretty easy to know the number of elements it has is 2. And now we define a k plus 1 based on a k for all k greater or equal to 1. We say it's a power set of ak. So in this case, we know A2 is equal to the power set of A1, which contains, well, empty set must be in it 0, 10, as they are separate as sets, and also the whole set as 0, 10, which has 4 elements. So there's 2 elements, have 4 elements, and we do the A3. A3 is the power set of A2, which is very, very complex because it will started with the uh the empty set, also the set of empty set here, and but this is the last writable set because it has the 16 elements, which is equal to 2 to the power of 4. And as we move on, it will be not very computable in the end because as we going on, it will have the A4 will have 2 to the power 16 elements based on the power set's definition. If there's 4 elements in the set, if there's 16 elements in the set, and the power set will have 2 to the power of 16 elements, which is 65,536 elements. That's too much for like writing them all out. So this is the last one I'll write it out. And based on this trend, we can find something very surprising about power set recursion, which is an is equal to power set of a n minus 1, which is equal to probably we can write is equal to p dot some dot p uh, a1. And there's many layers, so how many layers there are? If there's an, if it's an, then there's because consider P1 has 1 layer, P2 has P1 A1 has 0 layer, A2 has 1 layer. So probably for an there's will be n minus 1 layers. So yeah, so that's the our finding. And how many elements there is actually a tower of 2. So we mean tower of 2 means there's like some power of power of power of power of. So in this case, it's 2 to the power of 2 to the power of 2 to the power of 2. And there's n elements, n times of the tower, n layers of tower of 2 elements. And this can be put here. So we can see the example A4, which is n equal to 4. And it's 2 to the power of there's 2 layers of tower, which is computed as 2 to the power of 2 to the power of 4 equal to 2 to the power of 4 is 16. So which is this one, as we get the result same. So we have already proven. So this is our so we end the discussion about the power set and move to our today's content. It's called functions. Okay. So I think all of you have know the function since middle school or probably higher school. Like function is usually studied as some wait a minute, some fx equal to something, which is like x2, for example, and this is what we call it a function. And this is a good way to define function as it has an input and it also have an output. But in college school of math, we define function in a more like in a more rigorous way, which can be stored as a set, which we use the set to define functions. How can we do that? So first, for every function, we usually use f to denote. That's like our tradition in high school. So we say from the set A to set B as a set of ordered pairs. So remember, a set of ordered pairs is like A, B, right? A, B, and given that A is in set A, B is in set B, is in set capital B, and this will be the ordered pairs, and F is a subset of ordered pairs, which vary like a relation, and it has a property that for all of the x in A, there exists only one y in B, such that x, y is in F. So how can we understand this? We can understand this in this way. So imagining A, B is in some function F. So for all A here, there must be one B. So if you already observe A1, B3, for example, you will no longer observe A1, B5 again because the pair with A1, the second coordinate pair with A1 is B3, so it cannot be B5 again. So this is how we define the function. So the definition of function is very important when we discuss the type of function, whether it's onto or one-to-one, because the second coordinate can pair with the first coordinate only once and is unique. So this is our definition here. Okay. And the notation, we use an arrow to denote it. So f equals to b or a equals to b by f means f is a function from set A to set B. In this case, set A is called the domain of a function. We denote by this dom f, and B is the codomain of the function. And all of the elements in A, which is called pre-image of the function f, all of the y in function B, which is y can be defined as fx because it's transformed by function s of the elements x. So y equal to fx in the set B, where x is in set A is called an image of x in function f. So x is the image, but it can also be like if we define fa, then this situation would say fa is an image of the domain A after the transformation f. So this can also be called image, and fx also called image. They are the same image. They are just the f conveys different things. This is conveys a single element, but f can also convey a whole set. Okay, so this is the image. And there's another terminology which is very similar to codomain. It's called range. So what is the range of a set? Let's say its C is equal to all of the points fx, with x is in the set A, and it's the range of f. So so this means like all of the elements in C is not all of the elements in B. It's not all of the elements in B. It's the elements in set B that only can be found the connection with set A by function f. So the image, the range is just a subset of the codomain. So in this picture, you can see it's very obvious. So this is domain of f. I don't know, the shape on the left is A, which is domain of F, and the larger shape on the right side is B, which is a codomain of F. And we can see there's the function f is paired with x1 to fx1, x2 to fx2, x3 to fx4, and x4 to fx3, f5 to fx3. So in this case, you can see, yeah, it is true that for every function x1, there's only one there's only one fx that can be found. Like if you say f1, what's the pair? It's fx1, right? If you say what's the pair of x4? It's fx3, and x5 is also fx3. So it's paired. It's a good pair. So it's a function. But if we say like f3 is also goes to fx4, then this is wrong. This is a wrong case because for the first coordinate x3, there's two value, which is not made the function. So this case is a function and the range is what x have reached by the function f. So range is actually consists of fx1, fx2, xs4, and fx3, and 5 and 6x is not reached. So all there belongs to the codomain because B is already defined previously. But obviously A A only the points in A only conveys to fx1, 2, 3, 4 in by function f. So that's the difference between the range and the codomain. Okay. So functions can also call mappings, maps, transformations. So this is what we already said. So if y equal to fx, then we say f transforms or maps x to y. But in elementary level, remember in the set level A to B, the donation is like that, it's an arrow. But in the elementary level, the notation might be slightly different as we will use f x go to y by f, which is we add a vertical line here. I would say this one is not the case we usually use, but it's correct. Usually you just use this to get rid of the f because we in most of the circumstances we already know what function is, whether it's g or f or h or whatever. So we already know it. Why we need to write it again? We just ignore it. So it's like x go to y in this case. So we see some special examples of the functions. So first one is identity function. Of identity function, as you can see, what's the identity integer? What's the identity element integer is one because everything times one becomes self. So one is called identity element in integer. If you study the abstract algebra before or just by sense, like so identity always means like whatever it transform, it always the original value. So what's the identity function? It's very simple. It's just like fx equal to x. As we can define from set A to set B, all of elements just goes to element itself. Then this is the identity function. We use fa to denote it. Okay. And the second function is also very special. It's called a constant function. This is like given any non-empty set A, and we say B has one element, which is B0, and there's only one element, and all of the element going from A to set B is going from A to B0. So in this case, f is called a constant function with the value B0 because it only conveys every value to a single value, which is constant. So this is a constant function. And the third special type of function is the transition function. So it's like, as we can say, um, it is a dimension reduction function. Like it goes two dimension, A times B, or a how to say, like a not partition but Cartesian with B goes to a singly. Okay, so in this case we say f goes from the element wise is like AB as a coordinate as a order pair goes to a single element uh, A with the special A. So which means like F turns a combination AB into another A, which is single in one dimensional. So in this case, the dimensional is decreasing. All right. And well, in this case, we can say the process of change from from A, B to A is dependent on B. So actually we can view it as like A is transformed into A special A, but it just depends on information stored at B. If we add B here, then goes to A1. If B change to C, maybe it goes to another different value a2. So b is like a threshold. If b examines what value a will change to. So it might change to the a itself, like the special is equal to a, or it cannot equal to a, just depend on the information on b. So this is the transition function we introduced here. And the fourth type is called truth function. So this function is not very commonly used in practice, but is familiar with you because you study the logics in the first lecture. So the truth function is just as it's a non-empty set, like as constructed as many proposition, then denoted as P1, P2 to Pn. So this is set S. And we have a function which is transformed from S to Tf, and this function, we call it a truth function, or we call it a truth value function. And in this case, fp for each p, if p is a true proposition, it goes to t. And if it's a wrong or false proposition, it goes to false, goes to f. So we can use this function as, in the first lecture, we studied something called like truth functional. So this is a truth functional thing because if p we examine here, p examined by the function is t, then p is true, and f and q examined by the function is f, so it's false, then p and q is always truth functional because f and t is always f, and f or t is always t. So t in this case, any truth function is truth functional, as its name indicated. And the last type of function, not the type of function, but the easy, simple example function, which can give you a start-up view about what function is the polynomial function. So let's say, define f going from R to R, which is like R here means real numbers. So if we find fx is in the form for each single element is in the form of an times x to power of n, and it goes from like each step is decreasing one, n minus 1 x to the power of n minus 1, n minus 2 x to the power of n minus 2, and there's more like minus 3 minus 4, and maybe goes to 5 4 3 2 1 0. And x is pure because x to the power of 0 is just equal to n, is just equal to 1, right? So this is why it is paired. So this is called the polynomial function, as is in the function is in the form of a polynomial. And something we'll notice here is that all of the a here is in R. Like all of the a goes from k equal to 1 to n is in R. And an must be non-zero, because if an is 0, then this term is 0, and this will be the leading term. So it's not. So we just can get rid of it. Why we need another term like an times xn? We just start from here, an instead. So this is why we cannot let an be 0 in the polynomial function. All right, and such function is called a polynomial function with degree n. And real numbers here, like we can find a0 to a1 to a2, a3 to an, they're called the coefficients of f, because x is variant, they're fixed, and some fixed value times some variant values, which is x here, is called coefficient in polynomial settings. Okay, and then after we study that, we might be interested in how can we define equality between functions, because we can define equality between sets, the equality between different statements, and the equality, what's the equivalence relation. So we have already defined those things before. So this trend might lead us to consider what is the equality between functions. So how we can say f, g to function, they are equal. So there's two conditions it must be satisfied. First is their domain must be the same. So if f domain is not equal to g domain, then they are not equal. And another thing is on the condition their domain is the same. So there's one more thing we need to make sure it is, which is like fx is equal to gx for all of the elements in the domain F, which is also domain G because they're the same. So all of the elements in their domain must be transformed to the same value after the two different function. Then we can say the two different function is exactly the same function. So reasoning is very similar. It's very easy. Okay, because remember, like the function f is what? It's a storage of some a1, b1, a2, b2, maybe a3, b2 for some repetition possibly occur, and it goes in this trend, right? So this is actually, oh, maybe this is a large bracket. So this is how f is stored as a function in their information. So the first condition confirms that all of the A1, all of the first coordinate A1, A2, A3 here, they're the same. So both in both F and G. So G here also the first, like if their domain is the same, it also defines. Oh, so first consider there's only three elements. So this one it doesn't exist. So it seems like uh this is F. Then what's the first condition? Domain F equal to domain G indicates, which indicates there's also A1 something, A2 something, and A3 something. Right. This is the first indicate. And what the second indicates, what's the second statement indicates, like fx equal to gx, then A1 must be transformed to the uh, uh same like f A1, which is B1. So G A1 is also B1, GA2 is also B2, GA3 always B2. So this makes sure they must have the same elements in the function set, which means f is equal to g. Uh, and exactly we're still doing the set comparison. Well, just like um what we did a relation comparison. Well, like if we compare a function for their equality, it is still doing the set comparison. All right, sounds good. So we can move to the next topic, which is the example. So let's say we have three functions. First, f is x squared minus 1, and the domain is R. G is x squared minus 1, but the domain is narrowed into Z. And H is x plus 1, x minus 1, domain is R. So in this case, we can obviously see like f and g, they're different because the domain is different. So it doesn't satisfy the condition one, which say if two functions are equal, their domain must be equal. So f is not equal to g. But we say then we found like g must not equal to h because the domain is also not the same, right? But how we can say like f is equal to h? Is it possible? Their domain is the same, so it passed the first condition. What about second condition? Like for all of the elements in R, x squared minus 1 is equal to x plus 1, x minus 1. So they are actually the same because the value passed in fx f and hx, they are maps to the same value as x squared minus 1. So that's indicate function f is equal to function h. Another small topic I want to talk about is the restriction. So let's say there are two functions. There's f and g, and the domain of f is a subset of domain g. Like it's much smaller than domain g. Then we can say like f is a restriction of g to a. Because like if this is based on the information we know, like fx equal to gx on the set A, which is a subset. So we say f is a restriction because we can see here if we know g is there, this is g, and we can like narrow the domain of g into only for larger than 0, then f is here. F is here. So it is a restriction on the domain, right? And we denote F as G vertical line A, and the vertical line here means the restriction. So G only based on A. And G might also call the extension of F to B because G is like they have the same value on A, but it has more information than F on another set, which is a difference with B. Okay, so in example above here, we can say like H and F, as they're the same, they're both an extension of G because they just expand G from the set Z to set R, from integer to real number. So F and H are, they are the extension of G to set Z, but is G a restriction of F and H? I would say yes. I think G is a restriction because they have the same value on the integer, just as like the G and F, they have the F and H, they're just extension from the integer to real numbers. So that's we call G is a restriction. They have the same value here. All right. Yeah, so let's introduce a theorem here. So if the sets A and B, they're fixed, so which means like, oh, we already know what A and B are. And for all the function f, the restriction from B to A is unique, but extension from A to B or B to some other domains is infinite in many cases. So this is easy to understand by the example in the next picture. So if we say B, in this case, we just denote like B is equal to R, the whole of real numbers. And we say A is just R plus, which is equal to like, let's say, yeah, here. This is A, which is X equal to R, and X greater or equal to 0. And this is our set A. And well, they're defined, they're fixed. And we need to find the restriction of some function on B to A. And restriction is the same because, for example, let's G or G1 denotes the function S squared. Then what's a restriction? A restriction is just the X squared. It's just X squared but just on the set A. So this means like because it's already fine here, then well then you must find exactly the same path, exactly the same function as the original one. But what about the extension of A to B? B is fixed, B is the real number, but it doesn't define how the function can go. So it can go as like that, as G3 it's a 1.6 can go this way because it doesn't say, well, this part will always be, but it can be x2 too. It can be x2. It can also be negative as a square of 2, square of x. So it can also go this way. It's just opposite. Or it can remain some constant value, 1.6, or it can go as a sine function. Or it might go some very weird function like that, but it's also working. So we cannot say how the function below outside of the set A is going when the function is an extension. So although B is fixed, the set is fixed, but there's infinite many values to choose. And yeah, and if you have like interest in this set, you can look at how the how we notice of the like uh how the word says here. So with domains 0 to infinity, and the domain G is more, and G restriction must be the same as F, so it's unique. But because G is already defined, and F's extension, there are many cases like those four can also be noticed. And notice function F going from A to B, not all elements of B are used, right? So in this case, Also, we say like G is going from probably R to R, going from R to R. But you can say, well, even though we say its codomains R, but its range is actually R plus. It's just the non-negative numbers because the square cannot going down to negative numbers. So in this case, we find there's some elements which is not found, or which is not used in the codomain set. So in this case, the range makes a big importance here. So the range is a subset of B, the codomain, and we denote the range by FA or the image, right? We can say it's the image or range, and FA is F element A for all element A, including the set A. And the range of function F is just like the B element being set B. There exists one element in set A such that the F transform the A into element B in B, which is also a subset of B. So there's two type of function. The one type is all of the elements in the codomains reached. Another type is like there's only part of it reached, and another part is doesn't reach. So there's two kind of function. The first is surjection. Surjection, how we define it, it just means like all of the elements in the codomains is reached by the function from the domain A. So if for all of function all of the elements in B, there exists one A in set A, which is domain such that FA is equal to B. So this is a surjection. And it also can be called onto because all of the element B is the function is onto the set B, like all of the B is reachable. And any surjective function has a property, the image of the set is equal to the codomain, or the range is equal to codomain, which is true. So let's give some examples of the surjective function. As we said before, s squared, the polynomial function x squared is not onto because for all of the x, y smaller than 0 and y in R, and R here denotes the codomain. There's some elements, all of the elements, which is smaller than 0 in the codomain. There doesn't exist a unique x such that in the R, and here R means this R, means the domain R. There's no elements in the domain R such that x squared is equal to fx equal to y. So it doesn't satisfy the surjections definition. And another function may be defined as this one. It also goes from real number to real number, and it's defined as x plus 1. This is surjective. This is surjective because if for all of them, y in the range R, there exists one x equal to y minus 1 in the domain in the R. This is because this is mainly because the real line is infinite. It can go to infinite negative and it can go to infinite positive, and this is R. So in this case, x is equal to y minus 1. It's always findable. Like you can always find for all of the y in R, you can always find, which means there exists one x equal to y minus 1, and it's also in R. Okay, so this is the surjective definition, and we'll go to the second definition, which is injective. So what is injective? Injective means like it's one-to-one relationship, which means like all of the elements in the domain goes to, maybe we'll say the opposite ways, like all of the elements in its codomain, maybe in its range, just related to one element in the in the domain. So we can write a picture like that. There's two, and there's also two elements. This is the domain, and this is ring. And this may be the codomain. Codomain. Okay. So if the going was like that, it goes to this one, this goes to this one, then this is a injection because all of the elements here they have only one linkage to the elements. But if we change it a little bit, if we yeah, what about this case? If these elements also go to this one, then this is not injective because there's more than one. Look at that. There's more than one elements in the domain, which is goes to a single element in the codomain. So this is not what we call the injection. So one way to check this is to find all of the A1, A2 in set A in the domain, such that if A1 is not equal to A2, then FA1 after transformation FA1 is not equal to FA2. So this case it failed because look at that. A1 is not equal to A2, but FA1, FA2 is the same value, which violates, which means it is not an injection. And another way to check it is to first to find, well, to find two common values in the codomain, FA1, F21, FA2. Then we can find A1 is equal to A2 in the domain set. And this is another way to check it. And let's say one example. So f going to from real number to real number with fx equal to x power 3 is an injection because if you have a chance to view the graph of the x to the power 3, it looks like that. Just look at that, right? And this x, this is fx, and this is x to the power 3. And we can find for each of the fx, there's only one x across the real number set, which in this case we say is 1-to-1, or is actually injective, because if A1 doesn't equal to A2, like this A1 this A2 doesn't equal, then the value FA2 doesn't equal to FA1. So this is why I say like this function is actually, well, it's actually injective, or is an injection. And another definition based on the definition of injective, injection, and surjection is bijection. So if function is both, if it's both surjective and injective, we say it's bijective. So notice some words using here. So function we can say is a bijection, it's a surjection, it's an injection, but we use injective, surjective, and bijective to describe its property. So another corollary regarding such three definitions is like a function f belongs to set A Cartesian with B. It's a bijection from A to B if and only for each A element A in set A occurs exactly once for the first coordinate, and the other pairs occurs exactly once for the second coordinate in the other pair. So which means like if it's a bijection, then what's the character inside the set? Which means like A1, A maybe B1. Okay, B1. And A2, B2, A3, B3, and it goes down to infinite. And the only rules it follows is that A must appear only once and B must appear only once. This is because like this is directly from the definition of function and injective. Because if there's two A1 related to something, then it's not a function. It will violate its definition. But if there's two like B occurs, like A1 equal to B1, A2 also what about if also equal to B1? It's a link to B1, then which means like for all of the elements A A1 not equal to A2, B1 equal to B1. So it violates the definition of a injection. So which means if it's not injection, then it's not bijection. So this is what a corollary says. Okay, so let's see example. So let's see this example. A equal to set 0, 1, 2, 3. B is A, B, C, D, E, A, B, C, D, E. 5 elements, 4 elements. So we define 4 functions here. So let's see first. We can observe that G and I, yeah, G and I, they are not function. They're not function because uh, there's there's one element in the domain related to 2 different elements. 0 goes to B, 0 goes to E, 3 goes to C, 3 goes to E, which violates the definition of function. And I here doesn't mean a function because not all of the elements in the domain is included in the function. So 1A, 2B, 3E, and 0 is not linked. So I and G are not even functions. Then we see function H. 0, 1, 2, 3 all included and it only appears once, or paired once. So this is a function at least. So we say if it's a surjective one, no, because it only reach A, B, C, but D and E is not reached. So it's not a surjection. It's injective. If it's injective, we say it's not because both 0 and 1 goes to a value A, so it's not injective. So it's just a common function. It's neither surjective nor injective. And function F, let's say it goes A, D, C, E. So it reaches A, D, C, E, but not B, so it's not surjective. But it's injective because for all of the elements in set domain, 0 goes to A, 1 goes to D, 2 goes to C, 3 goes to E, and each pair is unique. It doesn't have a situation like two different values like 0 and 1 goes to same value in the range. So in this case, we say it's well, it's a injective function, but because it's not surjective, only injective, it is not bijective. And one fun thing is to observe is if you continue to choose A as a domain and B as a codomain, then there's impossible to form a bijection. This is mainly because it doesn't possible to form a surjection. Because surjection, which means all of the elements is reached, and you only have 4 elements, and each one can only use one to reach each of them. So in this case, it means like there's at least one element in set B in the codomain which is not able to be reached by elements in set A. So you cannot form a surjective function or bijective function based on this one. So one application of the function is index set. As we discussed index set before, like index set is a set I that mainly contains the natural numbers 1, 2, 3, 4, 5, and we can use another set to be useful, like b equal to bi for all of the I equal to I, the capital I, which is index set, and with I equal to 1, 2, maybe goes to 1,000. So this is a index set. And function can also represent index set. And this is one very important application of functions. So let's say S and I are 2 non-empty sets. So define a surjective function, which is like I goes to S. So which means every element in S is reached by at least one, or yeah, at least one element in I. So, and in this case, F, the function F, going from I to S is indexes that set S by I. So typically we use Si to denote Fi, the function Fi. So what does it mean? So let's see one example. So CR denotes a circle with radius R centered at 0, 0. So is CR means like that. So this is centered 0, 0. And the radius here is R. The distance is R. So this is what example shows. And let set S be all of the circle in this way. and I is equal to some elements, which is positive. X is in real numbers and is non-negative. So for all of the x in I, fx is going from fx also denoted by small s x is cx. So the x we picked here is just the radius in the set S, in the circle in the set S. So x is the index set for S. So this is the index set definition in by a function's view. And by now, we can do some other operations on the functions. So one very famous one is composition of functions. It's just like adding two functions and form a new one. So we can say, so we first define the function f and function g, and f goes from set A to B, g goes from set B to C. And for all the element x in A, y in B, z in C, the composition of f and g is we use this character some small circle. So G composition with fx is become this one. And just because fx is equal to y instead of b, so we also use gy to simplify it. And the graph looks like in the next page. So this is a graph looks like. So f goes to b from set A to set B, and element in B called y goes to element z in set C. And this is go from f and g, but it can also goes from a composition function. So first going from f and g. So which is like first f and then taking g above f. So this is like a sequence of function. It has a sequence. So first compute f then g, but if we reverse the relation, like if we want to do g first then f, then we should write this one. And this is not equal to g equal to composition with f. They're not equal. So the sequence, the order is really matters in this case. All right. So, and we can, in this case, we can see the composition function transition from A to B and B to C is actually A to C. And the domain of G and F composition is just the domain of F because G is based on the F's codomain. So the domain of GF is just the domain of F, which is A here. Okay, and another fact here is like what's the composite function is all of the function that can be expressed as a composition. I think here is actually every function is a composite function. So if give you a function, you can say it's composite. So I will explain this fact later, but this is a very fun fact. So there are some examples about functions uh, composition. So let f goes from real number to real number and is x squared plus 2, g x squared plus 4. So we can see f. So first consider g and then f is x to the power of 2, x squared plus 4 squared plus 2, which is x to the power of 4 plus 8x squared plus 18. But if you do the opposite side, first do the f and then do the g is x squared plus 2 squared plus 4, which is, well, different from the answer we get here if we plug in different x. So in this case, we can say, because this counterexample exists, this is a counterexample for us to conclude this conclusion. So fg doesn't equal to gf in composition. So the order in the composition of functions matters. Okay, and another function, but this is, we say it's not equal. It's a general case, but there are some special cases which f, g, and then g, f in composition, the order doesn't matter, but it's just some very special cases. So we can say here, let's do f, we say f going from the two-dimensional real line, which is x square coordinate, is transformed from an xy coordinate to another xy coordinate, and g is transformed from the same thing. So in this case, we say, well, they're doing very constant. So what f do is goes from it transform a set of function xy to x0, and g doing is it transform xy to 0y. So this function f and g here is called a projection of something because originally it has two dimensions, but transform f well only has one dimension. It goes to x dimension, and what g do is like first it's a two-dimensional point, but after g it goes to y. So it only have this one dimension, which is the second dimension y. So they are called projection because it reduces the dimension. And in this case, if we do first do f and then do g, we reduces the dimension twice. We become zero dimension, which is 0, 0. And if we first do g and then do f, we reaches the same, which is 0, 0 again. So f first g then f, and the first f then g is the same in this special pair of g and f chosen. And we can do the composition of function. We can also do the inverse way or the converse direction, which is a decomposition of functions. So we can always express this function as compositions of simpler ones, like the procedure of factorizing integers into a product of more integers. So for example, if you do 6 times 3, 18, you can express as 6 times 3, and you can also express as like 6 times 3 times 1 times 1, right? And if there's some integer like 2, which is prime number, you can also do 1 times 2. So you can always do product of integer, factorizing of integers just by identity. So you can always add 1. And the idea in functions composition is also very similar. You can always do the procedure of decomposition because you can also factorize into some like identity functions. So for example, like fx equal to x to the power 3 minus 3 to the power 5 as a total. So we can write, first we write this one. So we decompose it into 4 simpler functions. So g equal to x to the power 5, which is the most outlayered, f x minus 3, which is this layer, I, while ix is the identity function here, which is very similar to the role of integer 1 in integer factorization. And j equal to x to the power 3, it's this layer. So we combine them together gradually. So you get, well, so we get, gradually we get this one. So we get, first get rid of j, which is x to the power 3, and identity function doesn't change anything. And h minus 3, and then to the power of 5, which is exactly the same as f. So in this case, we have solved it successfully. And also, like, I would like to say, let me think about it. So why I always work. So why the identity function always work. So consider a function which is very simple, like fx equal to x. So it seems like it cannot be a decomposition because it's already very easy. But here we can always consider g times hx, and hx equal to x, gx equal to x. So what happened is and like g h x equal to gx because h fx, okay, hx becomes x, so it's gx, and gx is also x, so it's x, so fx equal to x. So any function, even the identity function itself, can be decomposed into 2 or more function because we can always use the identity function. Okay, another theorems like because we see above, like function composition is not commutative, which means like g f not equal to fg, but it is actually associative, which means like we first do g and f, then do f and g, h and g. They're the same. So this is a which means like function composition is associative. And the proof, the main idea is to just deduce uh is the definition of function decompositions. So first let's assume like the domain of this one is just the domain of G and F because the domain of a composition is always based on the first function. So G and F is the first function, right? And this one, F is again the first function. So which is F. And in this part, F is first. So domain of F is also equal to this one, the domain of H, G, and F. And this is equal to A, which is the domain of F. So they're not equal. So we only need to show for all elements in A, the two function transform is the same. And this is just very simple if we can use the definition of function composition. So we just do it one by one. We can also transform this form into this to the standard form and this form to the standard form. So they're equal. All right. And there are some basic properties of composite function as well. So if f and g are injections, then g, how to say like g um composite with f is also injective. If they're surjective, then it's also surjective. If they're bijective, then they're so bijective. And the fourth property we'll explore later. So what it actually means is that uh, for two different functions, if they satisfy injection, surjection, or bijection, their composition is also the same. So their proving process is very similar, but we'll see one of them for time. So so we'll prove the first one. So how to prove the GF is injective? So we'll prove like for all of the A1, A2 elements in the domain. After the transformation, after the function G composite with F, if A1 not equal to A2, then it will then this one is also not equal. So we just use the definition of injective because F is injective. So this one, make sure. But G is also injective. So if we put G outside of the not equal, this as the input elements, then this is not equal. And this one can be rewrite by the definition of composition, function composition. So comes this one. So actually here we do prove like if A1 not equal to 2, then GNF A1 is not equal to GNF A2 for all of the A1, A2 in A in the domain. So we have proved it. So the next very interesting property we'll talk about is the inverse function. So inverse function is only defined when the function is bijective. So let f equals to b be a bijection. We can define inverse of function f, the inverse of a bijective function, which is f minus 1. And this means like for all of the b into all the elements in set b, they're backtracking to a as original. So f1, f minus 1, which is the inverse of f, inverse of the bijective f, is defined as b a belongs to the Cartesian product BA, set BA. And originally they're just from A being F. So they're just inverse. So some properties of the inverse function is if the function F is bijective, that's where the inverse function is defined. Then F minus 1 is also bijective. And also second property is that if FA equal to B, then AB equal to F. Yeah. And this step, if AB equal to F, which means BA equal to inverse F, And inverse f, which means like inverse f taken b is equal to a. Okay, so this is actually what is the inverse function. And by using this fact, we can review the property, the force properties of constant function. It's like if f is a bijection, energy is equal to the bijection's inverse, which is the inverse of f. So if g equal to the inverse of f, then g composite with f is the is IA, which as we say, IA is the set domain of f, and IB is the set domain of g. So which means like if there's well A or IA, this set is called IA, and this side is IB. And F is typically moving from IA to IB. But if we doing a F, first doing F, and then doing a G, which is inverse F, then doing back, we get IA. And if we first do a inverse of F, which is from IB to IA, then do a F in the end. So it goes to IB again. So this is actually what the composite function and its inverse is related.